Welcome back to the Deep Dive, powered by Neural Intel. Today, we're plunging into one of the most persistent and fascinating challenges in artificial intelligence. How do we get models to truly understand the visual world around us without, well, the monumental, almost impossible task of manually labeling endless amounts of data? I mean, imagine the sheer volume of images generated every single day, from your smartphone to satellite feeds, medical scans, even particle accelerators. How on earth do we make sense of all that information without an army of annotators categorizing every pixel, every object, every scene?
It's a huge bottleneck,
Yeah.
a fundamental problem.
Well, the revolutionary answer emerging from the cutting edge of AI research is something called self-supervised learning, or SSL. And for this deep dive, we're going to unpack a major milestone in that journey, DINOv3. This isn't just another incremental update. It's pitched as a truly versatile vision foundation model, designed to learn powerful visual representations from diverse, unconstrained data, all using a single, elegant algorithm. Okay, let's unpack this and get into the technical heart of what makes DINOv3 so groundbreaking.
That's right. And here at Neural Intel, our mission for this deep dive is precisely that. We want to unravel the technical breakthroughs that make DINOv3 so incredibly powerful. We'll explore everything from its unique approach to data handling and curation to its innovative training strategies. The goal is to understand the why behind these advancements, how it learns from raw pixels, and the far-reaching technical implications. What happens when a model can achieve such capabilities without explicit human labels? As always, we're focused on the core technical details and the engineering brilliance behind these systems. And of course, you can always find more deep dives into the latest AI and ML research papers on our webpage, neuralintel.org, and check us out on YouTube for more in-depth analyses.
Perfect. So let's start with the foundation. Why is self-supervised learning, SSL, being heralded as the future of computer vision? What problem is it actually solving? Because for so long, AI vision models have relied on us telling them what they're looking at, right?
Exactly. At its core, SSL tackles that massive bottleneck of manual data annotation. Historically, for an AI model to learn what a cat is or a car or, say, a tumor in a medical image, humans had to painstakingly draw bounding boxes or segment outlines or label entire images. We call this fully supervised learning. And while it's incredibly powerful, it's just inherently limited by the sheer labor and cost involved, creating high-quality, perfectly labeled datasets. It's simply not scalable for the amounts of data we generate today.
Just doesn't scale.
No.
And then there's weakly supervised learning, which tries to get around this by using more readily available metadata, like image captions on the internet. But even that has its limits, doesn't it? You might know there's a cat and a ball in an image from the caption, but the model still doesn't know exactly where they are or how they interact at a pixel level. It's more about broad understanding, not granular detail.
Precisely. Weakly supervised methods, like those used for large image text models, they're excellent for global understanding, knowing what general concepts are present, like beach scene. But when you need precise, detailed, pixel-level understanding of a scene, they often fall short. This is where SSL truly shines. It's about letting the model learn directly from the inherent structure and patterns within the raw image data itself. No human-provided labels, not even captions. DINOv2, which was DINOv3's predecessor, really exemplified these strengths. It was almost like the model was teaching itself how to see rather than us telling it what to see.
Okay, so what were those core advantages that DINOv2 demonstrated and that DINOv3 is now pushing even further? What did we learn from that initial leap?
Yeah, there are several key advantages that make SSL such a game changer. First, there's scalability. SSL unlocks the ability to train on truly massive raw image collections because you don't need human labels. Think about the billions, literally billions, of images publicly available online or sitting in scientific archives. With SSL, that data becomes virtually unlimited training material. That's absolutely crucial for building large-scale visual encoders. You can just throw data at it, and it finds patterns.
Right, the data's already there.
It's there. Second, robustness. Models trained with SSL tend to be incredibly robust to what we call input distribution shifts. This means they perform well even when the data they encounter in the real world looks slightly different from their training data. They learn more fundamental, generalizable features that aren't just tied to specific training conditions.
Which is vital for real-world use.
Absolutely. Third, and this is where DINOv3 really stands out, is feature quality. They provide strong global and local features, generating these rich embeddings that facilitate physical scene understanding. While global features are good for overall image classification, knowing there's a dog in the image, strong local features are vital for tasks like object detection, segmentation, understanding 3D geometry. basically knowing where the dog is and the precise boundaries of its fur. DINOv3 was impressive, but DINOv3 makes a significant leap here, especially in this dense feature quality.
Okay, dense features. We'll definitely come back to that.
And finally, versatility. Because these models aren't trained for any specific downstream task, they produce versatile and robust generalist features. This means a single, frozen backbone, the core feature extractor part of the model, can serve multiple purposes. You don't need to fine-tune a massive model for every new application, which saves enormous computational resources. It's like having one universal visual intelligence that you can then easily adapt for specific jobs, like a Swiss Army knife for vision.
And that's a crucial point because traditionally, the focus for vision models was often just about getting the highest accuracy on ImageNet, which is a global image classification task, right? Tell me if it's a cat or a dog. But you're highlighting that SSL, particularly with DINOv3, offers this unique promise of high-quality, dense features. Can you break down what dense features actually means a bit more? And why getting them right at scale has been such a persistent challenge?
Absolutely. Dense features refers to the model's ability to generate a rich, meaningful representation for every single patch or pixel of an image, not just a single aggregated representation for the whole image. So imagine an image of a bustling street scene. A dense feature map would assign a distinct, semantically meaningful feature vector to each tiny patch. So a patch corresponding to a car gets one type of vector, a patch for building another, a tree, even the texture of the road surface. Traditional models, especially those optimized just for ImageNet, often prioritize global context, the what of an image. They might tell you there's a car, but not its precise boundaries or, the license plate details.
Right, they summarize too much.
Exactly. Achieving high-quality, dense features at scale is difficult because the model needs to maintain pixel-level consistency and fine-grained spatial understanding across a vast diversity of images. And it needs to do this even as it tries to learn higher-level, more abstract concepts. Historically, the objectives for global understanding could actually conflict with the objectives for local precision. It's a tough balancing act. And if you look at the paper's findings, Figure 1b specifically, DINOv3 shows a remarkable 22-34% relative performance improvement over weakly supervised models on dense tasks. That's a huge leap. It really shows the potential of this paradigm shift. It's about learning to see the whole picture and every brushstroke within it.
So where is this kind of high-quality, label-free, dense feature learning most needed? What are the practical domains where this really shines, beyond just, everyday photos?
Oh, it's particularly suitable for domains where large, high-quality human-labeled datasets are incredibly difficult or expensive to obtain, or they simply don't exist in the necessary volume. Think of highly specialized visual data. For instance, histopathology, looking at microscopic images of tissue slides. Super detailed, needs expert eyes. In biology, analyzing intricate cellular structures, again, very fine-grained. Medical imaging, like X-rays or MRI scans, which are highly sensitive and require expert annotation that's both time-consuming and, frankly, prone to human error. Then there's remote sensing and astronomy, where you have just vast amounts of satellite or telescope imagery with extremely limited human labels. Or even high-energy particle physics, analyzing detector outputs to understand fundamental forces. These fields generate petabytes of data, but they lack the metadata or human annotators to make traditional supervised learning feasible at scale.
So the implication is pretty profound then.
Yeah, DINOv3 suggests a future where AI can analyze highly specialized visual data in these fields without direct human intervention for labeling. This could lead to potentially transformative scientific breakthroughs. It sort of democratizes the ability to apply powerful AI to new, data-rich scientific frontiers.
Yeah.
It's almost like bringing a truly perceptive AI assistant into a lab or observatory where there was none before.
That sounds incredibly promising. Okay, but if SSL is so transformative, why hasn't it just scaled to arbitrarily large and powerful models easily? What were the challenges that DINOv3, for all its strengths, started bumping into at larger scales?
This raises an important question. If you keep training these models for a very, very long time, how do you prevent those crucial fine-grained features from actually degrading? That's a critical point, and it highlights the complexities of pushing these models to the bleeding edge. It's not straightforward. Even with DINOv2's innovations, three main challenges emerged when attempting to scale further. First, it becomes incredibly difficult to collect useful data from unlabeled collections. Sure, data might be unlimited, but not all of it is equally valuable for learning robust visual features. Simply throwing more raw data at a model doesn't always translate to better performance. You need high-quality, diverse, and meaningful data. Garbage in, garbage out still applies.
Quality over just quantity.
Precisely. Second, in typical large-scale training practices, especially with very long runs, researchers often use what are called cosine schedules for hyperparameters like the learning rate. This means the learning rate gradually decreases over time, but it requires knowing the optimization horizon a priori. In other words, you need to guess how long the model should train to get the best results. For massive, unconstrained image corpora, that's incredibly difficult, if not impossible, to determine beforehand. You might stop too early, leaving performance on the table, or train too long and risk degradation. It's like trying to perfectly time a marathon when you don't know where the finish line is.
Yeah, that sounds like a major headache.
It is. And third, and this is a known but largely unsolved issue that DINOv3 directly addresses. The performance of dense features, those crucial pixel-level representations, gradually decreases after early training, especially with models larger than the VT large size, which is around, 300 million parameters. You start to see visual degradation in what are called patch similarity maps. These maps show how similar tiny local patches within an image are to each other, crucial for detailed scene understanding. It's almost as if, as the model learns more global context from longer training runs, it starts to lose its fine-grained local consistency. Gets a bit blurry on the details. This significantly reduced the usefulness of scaling DINOv3 to truly massive architectures for tasks requiring precision.
Fascinating. So this isn't just about throwing more data and bigger models at the problem. It's a deeply technical challenge of how the model learns and retains information at different levels of granularity. It's about building a better brain, not just a bigger one. And that leads us directly into part 2. The engineering under the hood, how DINOv3 tackles these specific scaling challenges. Let's walk through some of these core contributions.
Absolutely. The first major contribution is what the paper calls Contribution A, which is a meticulously designed data preparation strategy. It's all about collecting truly useful data from massive, unlabeled sources. They started with an absolutely enormous pool, 17 billion Instagram images.
Cool.
17 billion. But crucially, they didn't just use them raw. Think of it less like simply collecting sand and more like sifting and shaping it into concrete.
Okay, so how did they sift through 17 billion images?
They constructed a sophisticated three-part dataset. The first part, called LVD1689M, was built using a clustering-based curation method. They applied a technique called hierarchical k-means to DINOv3 embeddings of these images, essentially grouping similar images together, creating this dataset of 1.689 billion images. The goal here was to ensure a balanced coverage of all visual concepts, meaning if there are obscure objects or scenes that occur less frequently, they're still represented. It ensures true diversity.
Preventing bias towards common stuff.
Exactly. The second part involved retrieval-based curation. Here, they retrieved images similar to a selection of existing well-known seed datasets, like ImageNet, for example. This ensures the training data includes concepts relevant to common downstream tasks, making the model more practical right out of the box. And the third part simply included raw public datasets like ImageNet1K, ImageNet22K, and mapillary street-level sequences to optimize for known benchmarks and ensure high-quality, established concepts were well represented.
So a mix of curated diversity, targeted relevance, and standard benchmarks.
Precisely. Then came the data sampling strategy during training. They used a hybrid approach, homogeneous batches, where all images come from a single source, like only ImageNet1K, and heterogeneous batches, mixing data from all three components. Critically, 10% of their training consisted of homogeneous batches only from ImageNet1K. This was inspired by observations that small, high-quality datasets can be incredibly beneficial, even when you have billions of other images. It's a very smart form of data engineering.
So it's not just more data, but smarter data mixing. And the ablation study in the paper, Table 1, really bears this out, right? It shows that no single curation technique works best on its own, but their careful mixing achieves the best of both worlds. What are the technical implications of this hybrid data strategy? How does balancing sheer diversity with targeted usefulness impact the model's generalization capabilities? Because this feels like a really nuanced approach to that age-old problem in AI. How do you get enough data without diluting the quality?
That's an excellent question to ponder. The technical implication of this hybrid strategy is that it allows DINOv3 to learn a more robust and truly generalizable set of visual features. By including the massive, diverse, yet carefully curated LVD1689M, the model is exposed to an incredibly broad spectrum of visual concepts. This prevents overfitting to narrow domains. It learns the underlying structure of visual things in general. A dog is a dog, no matter if it's a blurry cell phone picture or high-res professional shot.
Yeah,
you know?
It learns the essence.
Exactly. At the same time, the inclusion of retrieval-based data, and especially those homogeneous batches from ImageNet1K, injects a dose of usefulness, relevance to common, well-defined vision tasks. This ensures that while the model is learning broad patterns, it's also effectively optimizing for features that are known to be discriminative and valuable for practical applications. This balance is critical. Without the diversity, it might specialize too much. Without the usefulness, it might learn features that aren't practically applicable. It's a sophisticated form of data engineering that moves beyond simply collecting more data to actively shaping the data for optimal learning.
Incredible. So they're not just finding images, they're actively sculpting the training data itself. Now let's talk about the sheer scale of the training itself. Moving on to contribution two. Large-scale training with self-supervision. What did it take to actually make this 7 billion parameter beast learn effectively? That's huge.
Indeed. And DINOv3 significantly scales up the model architecture compared to its predecessors. For the learning objective, DINOv3 employs a discriminative self-supervised strategy. It's a sophisticated blend of several objectives. Think of these as different training signals or lessons the model learns from simultaneously. It incorporates LDNO, which is an objective focused on image-level understanding, getting the overall gist of a picture, and also LBA, which refines its understanding of individual image patches, ensuring local detail. Plus, they added LD-Coleo, a regularizer that ensures features within a batch are uniformly spread in the feature space, preventing the model from collapsing into trivial solutions where all features look the same.
So multiple teachers essentially guiding different aspects of learning.
Pretty much. They also made key changes from DINO2. Instead of Dino's original centering mechanism, they adopted an algorithm called Sinkhorn-NOP from SovUAV. It's known for its effectiveness in self-supervised learning, helps the model to better balance its internal feature representations, and crucially, they added dedicated layer normalization applied to the backbone outputs of the local and global crops. Empirically, this seemingly small change was found to stabilize ImageNet KNN evaluation and significantly improve dense performance. We're talking tangible gains. Plus 1 MIOU on 80/20K segmentation, -0.02 RMSE on NYU-V2 depth estimation. Small numbers, big impact.
Wow, those details matter.
They really do at this scale. In terms of updated model architecture, they scaled up to a truly massive 7 billion parameters. DINOv2's largest was 1.1 billion. This isn't just more layers, it's a significantly wider and deeper network. They used a custom vision transformer variant with axial rope or rotary position embeddings. This substantially improves the model's robustness to varying resolutions. Imagine a model that can look at an image zoomed in or zoomed out and still understand it equally well. They also opted for a patch size of 16 pixels, which affects the effective sequence length for a given resolution. And of course, the internal dimensions, embedding dimension, FFN, hidden dimension, attention heads, were all significantly increased to accommodate this scale.
That's a huge leap in model size and complexity. But what about the optimization strategy? This is where it gets really interesting because they departed from common scheduling practices, like those cosine schedules you mentioned. They opted for a constant learning rate, constant weight decay, and constant teacher EMA momentum for 1 million iterations. Why ditch such common scheduling techniques for a constant approach? Wasn't that like flying without a net, given how sensitive these large models can be?
It was a bold move, yeah, but it seems to have paid off. The traditional practice of using cosine schedules or other decaying learning rates implies that you have a predefined optimization horizon, or at least estimate how many steps or epochs your model needs to train optimally. But for truly vast, unconstrained datasets, it's virtually impossible to know that horizon beforehand. When do you stop? You might stop too early, leaving performance on the table, or train too long and risk that feature degradation we talked about.
Right, the unknown finish line problem.
Exactly. The constant hyperparameter strategy has two main benefits according to the paper. First, it allows them to continue training as long as downstream performance continues to improve. There's no fixed endpoint. If the model is still getting better on key tasks, they just keep going. This is a game changer for frontier models, allowing for open-ended exploration. Second, it reduces the number of optimization hyperparameters you need to tune. Fewer knobs to fiddle with, making the training process simpler and less prone to hyperparameter sensitivity issues. They still used a linear warm-up at the start for stability and employed the AtomW optimizer with a total batch size of 4,096 images across 256 GPUs, along with the multi-crop strategy.
That's a fundamentally different way to think about large-scale training, less guesswork. But how does such a large model maintain stability with constant hyperparameters, especially when prior attempts to scale SSL models faced known instability issues? I can only imagine the challenge of keeping something so massive stable without those traditional guardrails. What did they figure out that others hadn't?
It's an excellent technical question, and the paper hints at a few answers without laying out, like, an exhaustive stability manifesto. One key factor is likely the combination of their meticulous data curation and the specific architectural choices. That dedicated layer normalization they added to the backbone outputs for both local and global TROPs. That was empirically found to stabilize things and improve dense performance. This suggests that maintaining healthy, normalized feature distributions within the model's layers is crucial for stability, especially when you remove the annealing effect of a decaying learning rate.
So better internal regulation within the model itself.
Seems like it. Additionally, the use of axial rope, which contributes to robustness across resolutions, might implicitly aid stability by making the model less sensitive to variations in input. The paper also refers to DINOv3 having heuristics to mitigate instabilities, and it's likely that those foundational improvements carried over and were further refined. While they don't explicitly detail every trick they use to overcome stability hurdles with constant hyperparameters, the success strongly suggests that the combined effect of data quality, architectural design choices, and the specific loss functions creates an environment where the model can continue to learn robustly without needing aggressive decay schedules. It implies a degree of inherent stability in the learning dynamics that DINOv3's design unlocks. Perhaps it's like building a bridge with a more inherently stable design, rather than relying on constant, careful adjustments to keep it from swaying.
Makes sense. A more robust foundation. It's clear that DINOv3's engineering advancements are significant. But even with all these innovations, we kept returning to this persistent problem, the degradation of dense features during extended training. You mentioned how classification accuracy improves, but segmentation performance declines for larger models after, say, 200K iterations. Visually, figures 5b and 5c in the paper show this, and figure 6 shows those patch similarity maps, those crucial indicators of local detail becoming noisier and less localized over training, illustrating this loss of patch level consistency. This sounds like a core flaw in scaling. How do they solve that?
It was indeed a major hurdle, almost a paradox of scaling. Global understanding kept improving, but the fine-grained, pixel-level stuff fell apart, made the models less useful. This phenomenon of degrading dense features was a known, but, as the paper says, unsolved issue that plagued earlier scaling efforts. This brings us to the core innovation of DINOv3, gram anchoring. This is contribution. The insight here is absolutely crucial. They identified a relative independence between learning strong discriminative features and maintaining local consistency. Basically, a model can be great at telling cats from dogs, discriminative features, while simultaneously losing its ability to accurately delineate a cat's fur from the background, local consistency. It's like a person who can recognize a tree but can't describe the texture of its bark or the shape of individual leaves. And DINOv3 found a way to bridge that gap.
Okay, gram anchoring. How does it work?
The solution they developed operates on something called a gram matrix. For those unfamiliar, a gram matrix is a mathematical construct that captures the style or texture of features, how they relate to each other, rather than their absolute values. Think of it like a map of all the pairwise similarities between tiny patches in an image. How similar is patch A to patch B, patch A to patch C, patch B to patch C, and so on for all patches. The objective of gram anchoring, LGram, is to push the student model's gram matrix towards that of an earlier model, referred to as the gram teacher. This gram teacher is simply an earlier checkpoint of the same network, one from a point in training before the dense features started degrading, when it did exhibit superior dense properties.
Ah, so it's not trying to directly copy the features themselves from the earlier model, but rather copy the relationships between the features. That's a subtle but crucial distinction. It's like saying, you don't have to draw the exact same picture, but make sure the style and texture are consistent with my earlier, better work.
Exactly. That is the aha moment. The paper states, quote, "The local features are free to move, provided the structure of similarities remains the same." This is a profound difference. Instead of forcing the student's actual feature values to be identical to the teacher's, which might hinder its ability to learn new global concepts, gram anchoring only constrains the relative similarity structure between patches. It says, keep your internal patch relationships clean and localized. Keep them crisp, like my earlier, better self.
Wow, that's elegant.
It really is. This LGram loss is applied as a refinement step after the initial 1 million iterations, LPRE, which is typically when the degradation begins. The gram teacher itself is updated every 10,000 iterations, essentially using a slightly lagged but consistently high-quality version of the student as its own guide. The technical implications are clear from Figure 7. This method primarily impacts the local feature learning. Larget loss decreases faster, fixing that blurry problem without interfering much with the model's global understanding. LDI loss is less affected.
That's incredibly elegant, the idea of repairing very degraded local features, even with late application of this objective. It's like a quality control mechanism for dense representations. And the impact on performance is dramatic, right? Figure 8 shows this. This isn't just a theoretical fix, it translates to real gains.
Absolutely dramatic. Gram anchoring significantly improves performance on dense tasks, with notable gains shown on datasets like ObjectNet. But they didn't stop there. They introduced an enhancement, leveraging higher resolution features. This was inspired by observations that weighted averages of patch features and feeding higher resolution images can yield stronger local representations. Their clever approach was to feed images at twice the normal resolution into the Gram teacher, and then 2x downsample the resulting features before computing the Gram matrix.
Whoa, okay, so the teacher gets a high-res view.
Right. This effectively distills the improved patch consistency of smoothed high-resolution features from the high-res teacher into the regular res student model. So the GramBrain teacher is learning from a more detailed, higher fidelity view of the image, and then guiding the student to produce similarly crisp and consistent features, even if the student's primary training resolution is lower. It's a way of saying, even if you're looking at the general scene, remember the fine details I saw when I was looking closely.
And the visual evidence in the paper, figures 9a and 10, really drives this home, showing those crisp features and great improvements in feature correlations, much less noisy. The paper also highlights in figure 9b that selecting the Gram teacher from early iterations, like 100K to 200K, is effective, while using a later one, like 1M iterations, is actually detrimental. Which makes perfect sense, because by 1 million iterations, the Gram teacher itself would have those degraded features you're trying to fix. So looking ahead, what are the next technical steps for improving dense features even further? Could this Gram anchoring approach generalize to other domains or modalities beyond vision?
Yeah, that's where the real excitement lies for future research. In terms of technical steps, one might explore more dynamic Gram teacher selection, maybe using an ensemble of early-stage teachers or even a meta-learning approach to predict the optimal anchor point for the Gram teacher based on the training dynamics. Also, exploring variations of the Gram matrix itself, perhaps considering higher-order statistics or alternative similarity measures, could yield further improvements. The paper notes their method helps with the coarseness from 16 pixel patches, so maybe future models could push for even finer patch resolutions or more sophisticated ways to aggregate features from multi-resolution inputs within the backbone itself.
And beyond vision.
As for generalization, the core concept of anchoring the structural consistency of representations could absolutely extend beyond vision. Imagine applying this to audio, where local consistency in spectrograms might degrade during long training runs of self-supervised models. Or in sequential data like time series, ensuring the relative relationships between features at different time steps remain stable. In multimodal learning, you might anchor consistency between modalities. The core insight that global discriminative learning can be decoupled from local structural consistency is powerful and seems broadly applicable. It suggests the blueprint for building more robust foundation models across diverse data types, not just images.
The technical elegance of Gram anchoring is undeniable. Okay, now let's look at how DINOv3 expands its horizons beyond this core training phase. We're talking about the post-training refinements that truly make it a foundation for complex computer vision systems. It's one thing to train a massive model, it's another to make it truly useful in practice.
Absolutely. This is contribution 4 in the paper, which covers several post-training steps. The first of these is resolution scaling. The base model is trained at a relatively small resolution, 256 by 256 pixels, which is computationally efficient for that massive pre-training phase. However, as you know, many real-world applications require processing images at significantly higher resolutions, 500 by 512 pixels or greater, to capture intricate spatial details. DINOv3 addresses this with a dedicated high-resolution adaptation step.
So how do they adapt it? Just show it bigger pictures.
Pretty much, but carefully. They extend training for an additional 10,000 iterations using mixed resolutions. This means the global crops, the main views of the image, are sampled from larger sizes like 520 by 512 or 768 by 768 pixels, and the local crops, the smaller zoomed-in views, are sampled from proportionate smaller sizes. Crucially, Gram anchoring is brought back into play here. The paper states that without it, the model's performance on dense prediction tasks degrades significantly at these higher resolutions. This adaptation step ensures that the model maintains consistent and robust feature correlations, even with the increased complexity of high-resolution inputs. Figure 11 illustrates this nicely. It's like teaching a model to see both the forest and the trees, even when the forest itself is vast and detailed.
Makes sense. Adapt it, but keep the quality control. And this leads directly into the next key post-training strategy. Model distillation, also part of contribution. 4. This is where the immense power of that massive 7 billion parameter frontier model gets transferred to a family of smaller, more practical models. Because a 7 billion parameter model is brilliant, but it's not something you can easily run on your phone or even a standard server.
This is incredibly important for practical deployment, yes. The DINOv3 family of models, shown in Figure 16a, encompasses a range of vision transformer variants, from VTS, small, up to VTH+, large one, and even connext-based architectures. The goal is to provide scalable solutions for diverse resource constraints and deployment scenarios, from edge devices to high-performance servers, a model for every need.
How do they distill the knowledge effectively from such a giant teacher?
The distillation process itself is very clever. Instead of relying on, say, an exponential moving average of model weights as the teacher, which is common, they directly use the fixed, pre-trained 7B teacher model to guide the smaller student models. This ensures the distilled models inherit the rich representational power of the massive teacher as much as possible. They also developed an efficient multi-student distillation procedure, shown in Figure 12. This involves sharing the teacher inference computation across all GPUs being used for distillation. This allows multiple student models, different sizes, different architectures, to train in parallel, using the same teacher outputs. This significantly improves speed and compute efficiency, as the heavy cost of running the large teacher inference is amortized across many students.
That's smart engineering. Share the expensive part.
Exactly. And what's truly remarkable is that the largest distilled student, the VITH plus model, achieves performance that is on par with the 8 times larger VIT7B model on many benchmarks, Figure 16b. This really validates the distillation process and suggests a powerful new paradigm. You invest heavily in training one very large, very high-quality teacher model, and then you can efficiently distill its knowledge into many smaller, highly deployable models. This radically changes the economics and accessibility of cutting-edge AI. You get the benefits of the huge model without the massive deployment costs for every use case.
A very practical outcome.
Definitely. Finally, as part of Contribution 4, they also tackled aligning DINOv3 with text. While DINOv3 learns purely from images, they trained a separate text encoder, using a known paradigm called little t, locked image tuning, to align with the DINOv3 vision transformer model, specifically the VITL version. This enables flexible and scalable multimodal understanding. The key technical detail here is that they combine both the overall image representation, the CLS token, with average local patch representations before matching them to text embeddings. This allows the model to align both global and local visual features to text, going beyond what many image-text models achieve. It potentially leads to improved performance on dense prediction tasks when combined with text prompts. It means you could ask a question about a specific part of an image using text, and the model might understand better.
This is truly phenomenal. Okay, so we've covered the data, the training, the anchoring, the scaling, the distillation, the text alignment, the whole engineering pipeline. So what does this all mean for DINOv3's actual performance across various tasks? You've said it achieves exceptional and state-of-the-art results, often without fine-tuning the vision backbone. That's a huge claim. It sounds like it's becoming a true generalist powerhouse.
It is, and the results presented in the paper back it up unequivocally. Let's break down some of the key findings, starting with dense features. Qualitatively, Figure 13 shows DINOv3 features are sharper, containing much less noise, and showing superior semantical coherence compared to previous models like DINOv2 or weakly supervised ones. They just look better, cleaner. This visual quality translates directly to quantitative superiority.
Okay, give us some numbers.
On dense linear probing, where you freeze the backbone and just train a simple linear layer on top for a specific task, the results are impressive. For semantic segmentation on 8020K, Table 3, DINOv3 VTL outperforms the best previous SSL model by over 6 MIOU points. On cityscapes, it's plus 2.5 MIU over AM radio V2.5. These are significant margins. For monocular depth estimation on NYUV2 and Kitty, DINOv3 also significantly outperforms all other SSL models, like reducing RMSE on Kitty by 0.278 compared to DINOv2. Now remember, these are results from a frozen backbone. No task-specific fine-tuning was done on the main model itself, only that small linear head was trained.
That's the power of good features.
Absolutely. For 3D correspondence estimation, Table 4, DINOv3 shows superior multi-view consistency. outperforming DINOv3 by plus 4.3% recall on AVI, geometric, and plus 2.6% recall on spare, semantic. Indicates a deep understanding of 3D structure. In unsupervised object discovery, figure 14, a task where the original Dino already set a high bar, DINOv3, with its cleaner feature maps thanks to gram anchoring, achieved a significant plus 5.9 core lock improvement on VOC 2007. This highlights semantically strong and well-localized features for finding object boundaries without any labels.
Even finding objects without being told what objects are.
Exactly. And even for video segmentation tracking, Table 5, as an image model, DINOv3 demonstrates remarkable temporal consistency. It outperforms competitors significantly on DINOv3, 83.3 JNF score, plus 6.7 points over DINOv2. It understands how things move frame to frame surprisingly well. And for video classification, Table 6, DINOv3 performs comparably to specialized video models like VJEPA2 on appearance-focused tasks, showing its versatility extends to the time dimension too.
Wow. Okay, so it's dominant on dense local tasks. What about global image descriptors? How does it stack up on general image classification and retrieval tasks where weakly or fully supervised models typically reign?
Here, DINOv3 also sets new benchmarks for SSL. For image classification, Table 7, the paper claims it's the first time that a SSL model has reached comparable results to weakly and supervised models. This is a monumental achievement for pure SSL, especially on out-of-distribution tasks datasets that look significantly different from the training data. Think ImageNet-R plus 10% over DINOv2, ImageNet-Sketch plus 6%, ObjectNet plus 13%. Huge gains in generalization. It also shows the best robustness to image corruptions. ImageNet-C.
So it generalizes better to weird or unexpected images.
It's exactly. For fine-grained classification, Table 8, DINOv3 achieves the highest accuracy on the difficult iNaturalist 21 dataset, 89.8%, even outperforming the best weakly supervised model, PCOR. It's good at telling apart, say, different species of birds, and for instance, recognition, Table 9, differentiating specific objects or landmarks. It shows strongest performance by large margins on landmark recognition, Oxford, Paris, in challenging domains like art historical image retrieval, Met, Amsterdam. It improved by a massive plus 10.8 points on the Met dataset over DINOv2. This demonstrates an exceptional ability to differentiate individual instances, not just categories.
Okay, so it's a generalist powerhouse across the board, local, global, instance level. But how does this translate when DINOv3 is used as a foundation for more complex computer vision systems, not just these probing tasks? What are the engineering advantages here for developers building real-world applications? Does the frozen backbone idea really hold up?
This is where the foundation model aspect truly shines. And yes, the frozen backbone strategy holds up remarkably well. For object detection, Table 10, using a standard detector called PlaneDT, with a frozen DINOv backbone, it achieves state-of-the-art performance, 66.1 mmAp on COCO. And it does this with much fewer trained parameters in the overall system, around 100 million trainable parameters in the detector head, compared to 300 million or more for other end-to-end trained models. This is a significant efficiency gain.
Less to train, faster development.
Exactly. Similarly, for semantic segmentation, Table 11, using a MASC2 former decoder on a frozen DINOv3, it equals state-of-the-art performance, 63.0 MIOU on 8020K, and improves on COCO stuff and VOC 2012 benchmarks as well. The paper highlights the challenge of using 16-pixel input patches for dense prediction. It could be coarse, but DINOv3's high-resolution adaptation and feature quality helps overcome this. Even for tasks like monocular depth estimation, Table 12, combining a frozen DINOv3 backbone with a depth, anything V2 architecture results in new state-of-the-art performance, validating DINOv3's strong sim-to-real capabilities. And in 3D understanding, Table 13, simply swapping DINOv2 for DINOv3 in an existing pipeline called VGGT yields clear and consistent gains across various 3D tasks like camera pose estimation and multi-view depth.
The pattern is clear. Plug in frozen DINOv3, get state-of-the-art results with less training.
Pretty much. The consistent success with a frozen backbone across such complex, diverse tasks really points to DINOv3 truly learning foundational general-purpose features. The engineering advantages of not having to fine-tune a massive backbone for every new task are immense. You get reduced computational costs for deployment, simplified development workflows, faster iteration, and the ability to combine a single, powerful vision backbone with lightweight, task-specific heads. This means broader applicability and accessibility for complex AI systems. You don't need to retrain the entire underlying intelligence. You just teach it the specific new skill on top.
That's incredibly impactful for real-world applications. Okay, now let's shift gears slightly to demonstrate the universality of DINOv3's recipe. The paper applies it to a very different domain, satellite imagery. Because if this approach is truly universal, it should work for more than just photos of cats and cars off the internet.
This is a fantastic demonstration of DINOv3's generalized learning capabilities, yeah.
Yeah.
For the pre-training data and benchmarks in geospatial, they pre-trained a DINOv3 7B model, specifically on SAT 493M. That's 493 million high-resolution Maxar RGB satellite images. A completely different data distribution. What's crucial here is they use the exact same hyperparameters as the Web DINOv3 7B model. They only adapted the RGB mean and standard deviation normalization for satellite images and adjusted the training length slightly. This consistency underscores the recipe's generality. They then distilled the 7B satellite model into a more manageable VDITL satellite model, just like with the web version.
Same recipe, different ingredients, how to do.
The results for canopy height estimation, Table 17, Figure 19, are striking. These satellite DINOv3 models achieve state-of-the-art performance on several datasets, significantly reducing mean absolute error, MAE. For instance, on the open canopy dataset, the error dropped from 2.42 meters to 2.02 meters. That's a big improvement. This task requires physically grounded understanding of height from pixels. And the finding here is interesting. Domain-specific pre-training using the satellite DINOv3 is stronger for these physically grounded tasks where sensor-specific priors and radiometric consistency are important compared to the web model trained on Instagram photos. Which makes sense, right? If you're trying to measure something physical like height from satellite data, training on satellite data helps more than training on cat photos.
Makes intuitive sense, but then when you compare it to the broader Earth observation state-of-the-art, tables 18 and 19, figure 18, it gets even more interesting, doesn't it?
It does. Both the frozen DINOv3 satellite model and the frozen DINOv3 web model set new state-of-the-art results on 12 out of 15 classification, segmentation, and horizontal object detection tasks across a range of challenging geospatial benchmarks. GeoBench, Loveday, DIOR. And here's the kicker. These results are achieved with only RGB inputs and a frozen backbone. They outperform models like Prithvi V2 and DOFA that use 6 or more spectral bands of data beyond just RGB and require task-specific fine-tuning. That's incredible efficiency and effectiveness for a general-purpose model applied to a specialized domain.
So the general web model is competitive even against specialized satellite models using more data.
For many semantic tasks, yes. This has profound broader implications for the design of geospatial foundation models. Historically, geospatial AI has emphasized heuristic techniques like multi-temporal aggregation or multi-sensor fusion, assuming that more specialized data or complex preprocessing is always better. DINOv3 challenges this. Its results show that general-purpose SSL can match or exceed satellite-specific approaches for tasks that depend on precise object boundaries, like segmentation or detection.
So there's this interesting split.
Exactly. It suggests a powerful complementary strengths dynamic. The domain-specific DINOv3 satellite model excels in metric tasks, like canopy height estimation, where sensor-specific physical properties matter. But the domain-agnostic web DINOv3 model achieves state-of-the-art results on semantic geospatial tasks, like finding roads or buildings, leveraging its diverse universal visual representations learned from the web.
It raises an intriguing technical question then. Why does a model trained on general web images perform so well on highly specialized satellite tasks, especially for semantic understanding? What does this tell us about the nature of learned visual features in DINOv3?
It's a great question. It implies that the features learned from diverse web data are incredibly abstract and robust. They capture fundamental visual patterns, edges, textures, shapes, spatial relationships that are universal across different visual domains, even domains with radically different characteristics like top-down satellite imagery compared to, ground-level photos. This universality is a testament to the power of pure self-supervised learning on massive, varied datasets. It suggests that perhaps the underlying grammar of visual information is more consistent across domains than we previously thought. This allows a model like DINOv3 to generalize across wildly different visual modalities. The model isn't just recognizing things specific to Instagram photos, it's understanding the underlying visual structure of the world, which applies everywhere.
That's a powerful statement about the core capabilities DINOv3 has unlocked, a truly foundational understanding. Of course, with advancements of this magnitude, building something like a 7 billion parameter model, there's always a discussion about the resources required. Let's touch on the topic of the environmental impact, framing it, as the paper does, as a technical measurement of the resources required for such large-scale AI advancements, rather than getting into a broader debate. What does it actually take computationally to build one of these frontier models?
Yeah, it's important to provide a factual understanding of the computational footprint. The paper details this in Table 20. Based on their methodology, which uses established practices like power usage effectiveness, PUE, of 1.1, meaning data center overhead is low, and a standard carbon intensity factor for the grid, and specifying a power consumption for the GPUs used, A100s and H100s.
Okay, what are the numbers?
For the DINOv3 SESM-B, pre-training alone, that 1 million step run we discussed it, involved over 61,000 GPU hours on these powerful chips. The estimated energy consumption was 47 megawatt hours, MWH. This translates to roughly 18 tons of CO2 equivalent, TCO2AQ. To put that 47 megawatt each into relatable terms, the paper notes it's like driving an average electric vehicle for almost 240,000 kilometers, or about 150,000 miles.
Wow, that's
Yeah.
significant for one training run.
It is. For comparison, DINOv2 had a much smaller footprint, around 9.7 middleweight and 3.7 TCO2EQ. Other very large models mentioned, like MetaClip, consume significantly more energy, reported at 160 milliwatts and 62 TCO2Q. So DINOv3 sits somewhere in the middle of recent large models. Now, the carbon footprint of the whole DINOv3 project, encompassing all the research, ablation studies, different model trainings, distillation, etc., is estimated roughly 9 million GPU hours in total. This translates to an estimated 2,600 tons of CO2 equivalent for the entire research effort leading to the paper. The paper gives another analogy. It's equivalent to about half of all Boeing 777 return flights between Paris and New York for one day.
That really puts the scale of these research projects into perspective.
It does. And it's crucial to note, as the paper points out, these figures generally only account for the electricity consumed by the GPUs during computation. They do not typically include other emissions, such as the energy required for cooling the data centers, beyond the PUE factor, the manufacturing of the GPUs and other hardware, or their eventual disposal. This highlights the immense scale of the computational infrastructure and the energy demands associated with training frontier AI models like DINOv3. It's a significant technical consideration that informs the real-world cost and feasibility of such advanced research.
Absolutely. A sobering reminder of the resources involved in pushing the boundaries. So we've taken a really deep dive into DINOv3 today, and what's fascinating here is how it represents such a monumental leap in self-supervised learning, from its meticulously curated data and novel training strategies, particularly that ingenious gram anchoring for preserving dense features, to its exceptional versatility as a frozen backbone, and its surprising applicability across diverse domains like geospatial imagery. It's truly a testament to what thoughtful engineering can achieve.
Indeed, DINOv3 truly represents a significant advancement and a major technical milestone in computer vision. It highlights the immense potential of self-supervised learning to, well, revolutionize the way visual representations are learned. It moves us closer to truly intelligent and adaptable AI systems. The ability to learn powerful, versatile features directly from raw, unlabeled pixels and then distill that knowledge into practical, deployable models. That's a game changer for AI development.
It certainly is. And as you, our listeners, reflect on what we've discussed today, here's a final provocative thought for you to consider. Given DINOv3's ability to learn such powerful general-purpose features from raw, uncurated data across different visual domains, what does this imply for future AI development? Could this self-supervised paradigm, perhaps with techniques like gram anchoring, unlock understanding in even more complex, unstructured data modalities beyond vision? Maybe in areas like scientific simulations, biological sequences, or even abstract graph data where human labeling is impractical or just impossible. What are the inherent simplicities, maybe in the learning objectives or the architectures that we are still uncovering that allow such profound generalization from unlabeled data?
Are there fundamental patterns across all data that SSL is tapping into?
Exactly. How might these breakthroughs change how you approach data analysis or problem solving in your own work, whatever field you're in? We encourage you to keep exploring, keep learning, check out the paper and the models if you can. And as always, dive deep into the fascinating world of AI with us here at The Deep Dive by Neural Intel. Thanks for tuning in.